Hi friends, this is Naresh. In this class, I am going to explain about engineering mechanics and the topic is centroid of an composite section. In this class, I will explain how to locate the centroid or center of gravity of this composite section. This composite section consists of a solid triangle, solid rectangle, and solid semicircle and hollow circle. Here I consider given problem as three models. That is problem 1. Problem 1 having only 3 dimensions, and problem 2 having having 3 solid sections as well as one hollow circle. Here both cases are same. Here I consider the reference axis are same, but in problem type 3 I consider reference axis here, and also the given diagram is in reverse shape. So in this class I will explain how to locate centroid or center of gravity of these three problems. In next slide I explain how to locate the centroid or center of gravity for this type, that is problem 1. First of all, the given section is split up into 3 parts. That is first section is square having dimensions base b equal to 60 mm and height or depth d equal to 60 mm. Therefore the area of a square equal to a1 equal to 60 into 60, that is the base into height. 60 by 60 equal to 3600 mm square. I consider as section 1. And coming to the second section, I consider section 2 as a semicircle having diameter from here to here, the diameter d equal to 60 mm and radius equal to half of the diameter, that is equal to radius r equal to 30 mm. The area of a semicircle equal to pi r square by 2. I consider this as section 2. Now I consider third section as a triangle having dimensions base b equal to 30 mm and height equal to 30 mm. Therefore the area of a triangle A3 equal to half into base into height, that is equal to A3 equal to half into 30 into 30. Here in this slide I want to explain some basic principles or basic formulas. These are very useful in our problem. Here the centroid of a square or rectangle lies at where its diagonals meet to each other. Therefore the given square or rectangle is symmetric about horizontal line and vertical line. Therefore the centroid lies at a distance of half of the base and half of the height. Whereas for circle the centroid lies at its center. Whereas the centroid of a triangle lies at a distance of base by 2 and height h by 3 to h by 3. Here the given triangle is isosceles or equilateral triangle. Here the given section is symmetric about vertical line. That means here the given triangle is symmetric about this vertical line. So therefore the centroid lies on vertical line. Therefore base by 2 and height equal to h by 3 to h by 3. So first of all the given height of a triangle split up into 3 parts. Now you have to consider 1 by third part of height from base, that is horizontal line from base to centroid. The distance is 1 by third of height, and from apex point to centroid the distance is 2 by third part of height. Okay, now this is a semicircle having radius r and diameter equal to 2r. Semicircle consists of one straight edge, this is a straight edge, and other one is curved surface. So you have to remember the centroid of a semicircle lies on symmetric axis. The given semicircle is symmetric about this horizontal line, therefore the centroid lies on this symmetric axis, and therefore the centroid lies half of the diameter, that is radius r and radius r, and horizontally the distance is 4r by 3 pi and r minus 4r by 3 pi. Carefully observe it. The distance between straight edge to centroid is always 4r by 3 pi. Okay, and the distance between curved surface to centroid from here to here, the distance is r minus 4r by 3 pi. So therefore the total length from here to here, the distance is equal to r, radius, and the length of a straight edge from here to here, the distance is 2r, that is diameter. So these formulas are used in our problem. Now I consider x-axis here and y-axis here, and this is the origin. This is in first quadrant, and this is in second quadrant. So here from here to here, this is positive x-axis, and from here to here positive y-axis, and from here to here left side the value of x is negative. So therefore in second quadrant you have to consider the values of x are negative, and the values of y in both first quadrant and second quadrant are positive. First of all, the given problem is split up into three components. That is, first one is a square having dimension 60 by 60. Already in previous slide we have discussed about this. So therefore the area of a square equal to 60 by 60 equal to 3600. Now I am drawing the diagonal lines to locate the individual centroids. So these are the diagonals, and this point is the intersecting point for diagonals. So therefore the centroid of a square lies here, and the centroid lies at a distance of x1 from y-axis equal to x1 equal to base by 2, so half of the base, and at a distance of y1 from x-axis from here to here, y1 equal to half of the height, that is equal to d1 by 2 equal to 30 mm. So x1 y1 are the coordinates of the centroid c1. And coming to the second section, this is a solid semicircle having diameter d equal to 60 mm and radius equal to 30 mm, and the centroid lies at a distance of x2 from here this point here to here, the distance is x2. So the distance between centroid c2 to y-axis is x2 equal to 4r by 3 pi. In previous slide I have explained about basic formulas, so from that slide I have written here as 4r by 3 pi. Already we know that the distance between straight edge to centroid is always 4r by 3 pi. So I written here as x2 equal to 4r by 3 pi, but I consider here negative sign because this semicircle is in second quadrant, therefore the values of x are in negative sign. So therefore I consider negative sign for second quadrant. Now y2 is the distance of centroid C2 from x-axis. From here to here the distance is y2, that is radius of a semicircle equal to y2 equal to r equal to 30. Now coming to the third section, that is a triangle having base b equal to 30 mm, base b equal to 30 mm and height h equal to 30 mm. Already in previous slide we have discussed about centroid of a triangle. The centroid of a triangle lies on symmetric axis, therefore this is the symmetric axis. So the centroid lies on symmetric axis, that is base by 2, here base by 2, and you have to split the height of a triangle into three parts. 1/3 part of height from centroid to horizontal line, the distance between centroid to horizontal base is equal to 1/3 of height, and the distance between centroid to apex point is 2/3 part of height. Here this is base by 2 and this is base by 2, and height h by 3 and 2h by 3. You have to observe carefully. From centroid to base always h by 3, from centroid to apex point is always 2h by 3. So two parts, this is one part of height, two parts of height. Total height h equal to 30 mm and base b by 2 because the given triangle is symmetric about this vertical line, therefore base by 2. Now the centroid C3 lies at a distance of x3 from y-axis. This is C3. So the distance between C3 and y-axis is x3. So x3 equal to the total base of a square equal to 60 mm minus the value of base by 2. So from here to here the value of x3 equal to total base 60 minus and base by 2. So therefore that is 60 from here to here 60 and base by 2 equal to 15. So total 60 minus 15 equal to 45 mm. So x3 equal to 45 mm, and from here to here the distance of centroid C3 from x-axis is equal to y3. So y3 equal to the height of a square, that is 60 mm plus h by 3. So from here to here you have to consider as y3. So y3 equal to height of a square, that is 60 plus and 1/3 of height of a triangle. So d1 plus h by 3. In next slide I have written these values in tabular form. From previous slide, from given figure, these are the section numbers, these are the dimensions, and these are the individual areas. These are the centroids, coordinates of centroids. So the rectangle, area of a rectangle A1 equal to B1 and D1 equal to 60 by 60, and area of a semicircle equal to pi r square by 2, and area of a triangle equal to half into base into height. So x1 y1, x2 y2, x3 y3. So this is a c1, so this is a x1 and this is y1, and this is a c2, this is x2 equal to minus 4 r by 3 pi, and from here to here this is y2, that is r equal to 30, and this is a c3, that is a, from here to here the value is x3, and from here to here the value is y3. From general expression, xc is the distance of centroid or center of gravity from y-axis, and yc is the distance of centroid or center of gravity from x-axis. Now yc equal to a1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3. Here the given figure is solid section, there is no hollow portions, so I consider solid sections as a positive sign, and the answer is yc equal to 33.29 mm. Similarly, xc equal to a1 x1 plus a2 x2 plus a3 x3 by a1 plus a2 plus a3, and the final answer is 20.17 mm. In this slide I will show the final location of centroid. C1, this is C1 is the centroid of a square, C2 is the centroid of a semicircle, and C3 is the centroid of a triangle. So C1, C2, C3 are the individual centroids, whereas CZ is the centroid of a entire section. The CZ lies at a distance of xc from y-axis and yc from x-axis. So from centroid to y-axis the distance is xc equal to 20.17, and the distance between centroid to x-axis is yc, that is yc equal to 33.29. so this is the final answer for this figure. In next slide I consider this problem same, but I added a hollow circle here. Now look at the centroid or center of gravity of the given shaded area. Question is same. In this problem again I consider as a square as section 1, that is 60 by 60, and I consider section 2 as semicircle and having same dimensions, and triangle as a section 3 having same dimensions, whereas I consider fourth section as a hollow circle here. This is a hollow circle having dimensions, diameter pi equal to 20 mm and radius r equal to 10 mm. So how to solve this problem and how to locate the centroid of this composite figure? First of all, the given figure is split up into 4 sections, that is first one is a square, second one is a semicircle, third one is a triangle, and fourth one is hollow circle. So please remember, you have to consider positive sign for solid sections. Okay, you have to consider positive sign for solid areas and negative sign for hollow areas. So the area 1, area 2, area 3 are solid, but area 4 is hollow, so you have to consider negative sign for area 4. Here I consider x-axis at bottom edge and y-axis at left side. So I am located here I am drawing the diagonal lines to locate the individual centroids. So C1, this is C1. C1 is the centroid of a square at a distance of x1 from y-axis equal to half of the base, that is 60 by 2 equal to 30 mm, and at a distance of y1 from x-axis, y1 equal to height, half of height, that is d1 by 2 equal to 30 mm. Now I consider second section as a semicircle. The centroid lies on symmetric axis, that is a horizontal line, and at a distance of x2 equal to 4r by 3 pi. In previous slide I have explained basic formulas. From that formulas I have written here x2 equal to 4r by 3 pi, and I consider here minus sign. Already I have explained in previous problem. Here the square lies in first quadrant, therefore x and y values are positive, but semicircle lies in second quadrant, that means the value of x is negative and the value of y is positive. Therefore I consider negative sign for x2, therefore x2 equal to minus 4r by 3 pi. So the distance between y-axis to C2 is 4r by 3 pi, and y2 equal to radius of a semicircle, that is r equal to 30 mm. And similarly I consider third section as a triangle having base b equal to 30 mm and height h equal to 30 mm. In previous slide I have explained about centroid of a triangle. The centroid of a triangle lies on symmetric axis. This is a symmetric axis, so the centroid of a triangle lies on this symmetric axis. This symmetric axis divides the base of a triangle into two halves, that is base by 2, that is 15 mm and 15 mm. So this is base by 2, and the centroid of a triangle lies at a distance of h by 3. h by 3 from base and 2h by 3 from apex point. Now C3 is the centroid of a triangle and lies at a distance of x3, that is from here to here, x3 from y-axis, x3 equal to total base of a square, that is 60 mm minus base by 2, that is 60 minus base by 2 equal to 45 mm. And y2, the distance of y2 from x-axis, from centroid to x-axis equal to y2. So y2 equal to height of a square, that is 60 mm plus h by 3. Please observe it carefully. So y3 equal to height of a square, that is 60 mm plus h by 3. So here I consider fourth section as a hollow circle having dimensions diameter pi equal to 20 mm and radius r equal to 10 mm, and the centroid lies here. The centroid of a circle lies on y-axis, so therefore the value of x4 equal to 0, because the centroid lies on y-axis, and the value of y4 equal to half of the height from here to here, y4 equal to 30 mm. In next slide I have written these formulas, these values in tabular form. From figure, the values are, these are section numbers, dimensions, these are dimensions, these are individual areas, these are the individual centroids. So first section is rectangle having area A1 equal to base into depth, that is 60 by 60 equal to 3600, and area 2 is the solid semicircle, that is pi r square by 2. A3 is the solid triangle, and A4 is the hollow circle. Already I have explained. Section 1, section 2, section 3 are solid sections. Section 4 is hollow section. So you have to consider A4 as a negative sign. From basic principles, yc equal to a1 y1 plus a2 y2 plus a3 y3 minus a4 y4 by a1 plus a2 plus a3 minus a4. So already I have explained, area 4 is a hollow section, therefore I consider negative sign for hollow sections, whereas area 1, area 2, area 3 are solid sections, therefore I consider as positive sign. The value of yc equal to 33.49, and similarly xc equal to a1 x1 plus a2 x2 plus a3 x3 minus a4 x4 by a1 plus a2 plus a3 minus a4, and the final answer is x equal to 21.41 mm. In next slide I will show the location of centroid. Now C1 is the centroid of a square, C2 is the centroid of a semicircle, C3 is the centroid of a triangle, C4 is the centroid of a hollow circle, whereas CZ is the centroid of a entire composite section. So therefore C1, C2, C3, C4 are the individual centroids, whereas CZ is the centroid of an entire composite section. The centroid CZ lies at a distance of xc, from y-axis. So from CZ to y-axis the distance is xc, and the distance between CZ and x-axis is yc. Therefore the value of xc equal to 21.41 and yc equal to 33.49. So CZ is the final location of centroid, whereas xc, yc are the coordinate points of centroid. In this slide I will explain how to locate the centroid or center of gravity of third model. Here I consider square as section 1 having same dimensions, and section 2 as a semicircle, and section 3 is a triangle having base 30 and height 30, and section 4 as a hollow circle as having radius 10 mm. Here I consider reference axis here. Now I am drawing the diagonal lines to look at the individual centroids. So here this point is C1 is the centroid of a square section at a distance of base by 2 and height by 2. X1 equal to base by 2 equal to 30 mm, and y1 equal to height by 2, that is equal to d1 by 2 equal to 30 mm. Whereas C2 is the centroid of a semicircle, lies at a distance of x2 from here to here, the value is x2 equal to base b1 equals 60 plus 4r by 3 pi. So from straight edge to centroid, the distance is 4r by 3 pi. Therefore x2 equal to 60 plus 4r by 3 pi, whereas y2 equal to half of the height, that is d1 by 2 equal to 30 mm. Now C3 is the centroid of a triangle So C3 is the centroid of a triangle, lies at a distance of xc sorry x3 equal to base by 2, x3 equal to base by 2, and y3 equal to here the centroid of a triangle lies at half of the base and 1 by third of height. Therefore, from this point, from centroid C3 to y-axis is x3. Therefore, x3 is equal to base by 2. This is x3, and y3 equal to from centroid C3 to x-axis. The distance is y3. y3 equal to height of a square, that is 60 plus h by 3. So d1 plus h by 3 is the value of y3. Whereas for for hollow circle, C4 is the centroid of a hollow circle and lies at a distance of x4. From here, from y-axis to centroid C4 is x4 equal to base of a square, that is x4 equal to b1 equal to 60 mm, and y4 equal to half of the height, that is 30 mm. Here observe here carefully, the centroid C1, C4, C3 lies on same horizontal line. Therefore, the values of y1, y2, y4, y1, y2, y4 are same. Here y1 equal to 30 mm, y2 equal to 30 mm, y4 equal to 30 mm. y3 is equal to 60 plus 15, sorry 60 plus 10, 70. So y3 equal to 70. These values are written in tabular form in next slide. From diagram, the values are here. See, these are the serial numbers or section numbers. Section 1 is rectangle, section 2 is semicircle, section 3 is a triangle, section 4 is hollow circle. So here also area 1, area 2, area 3 are same and consider as positive sign for solid sections, and area 4 is a hollow circle, therefore I consider here as a negative sign for area 4. These are the x and y values for individual coordinates, individual centroids. From general expression, xc equal to a1 y1 plus yc equal to a1 y1 plus a2 y2 plus a3 y3 minus a4 y4 by a1 plus a2 plus a3 minus a4. So yc equal to 33.49. Okay, here I consider negative sign for area 4 because it is a hollow section. Okay, please remember. Now xc equal to a1 x1 plus a2 x2 plus a3 x3 minus a4 x4 by a1 plus a2 plus a3 minus a4. Therefore xc equal to 38.59. This is the final answer for this problem. Now in next slide I will show the location of centroid. C1 is the centroid of a square, C2 is the centroid of a semicircle, C3 is the centroid of a triangle, C4 is the centroid of a hollow circle, whereas CZ is the centroid of an entire composite section at a distance of xc from y-axis, x equal to 38.59, and yc from x-axis, that is yc equal to 33.49 mm. So this is the final position of a centroid. So CZ is the centroid of an entire composite section. So the final coordinates of a centroid CZ is equal to xc and yc. Okay, thank you.